Today's session from my side is, let's say, the initiating point of this whole process that this school is going to deal with. So it is about the path from research to innovation, but not in the simplistic sense of, okay, how do we commercialize an idea? But I want to focus in something deeper, how knowledge becomes capability and how capability becomes technology. And after that, how technology creates value. So the central idea is simple. Many of the technologies that shape our lives did not begin as products. This is not always obvious. Okay, they began as questions. So let me begin with a question. I want you to think of a transformative technology you used today or yesterday, and that it has foundations that do not rely on basic research. Think of your phone, think of a GPS, think of the wireless network that we are using now, or any medical imaging that you have used recently, artificial intelligence models that you maybe use. It becomes very difficult to find a truly transformative technology that does not rest on some deep layer of basic research. So, of course, technologies also require engineering, design, market, regulation, investments, everything. But my point today is that the foundations of most transformative technologies go back to scientific questions that were often asked long before any commercial application was visible. So this is not a romantic defense of research on its own sake. It is it wants to make a realistic argument that without deep knowledge, the space of future technologies shrinks. The talk has four parts. First, we will clarify what basic science is and why it is often misunderstood. Then we will look at the usually long road from curiosity to technology, and I'm going to provide some concrete examples that hopefully they will convince you. And after that, we will discuss emerging technologies. So what today's basic science is expected to become a platform tomorrow. And finally, we will move to the more, let's say, hands-on and technical part, which is how we turn this knowledge to value through innovation, readiness, knowledge transfer, etc. So the structure, in short, is concepts, stories, future technologies, and readiness. Okay, so let's begin with the first question. What is basic science and why it is often misunderstood? A good starting point is the distinction between basic research and applied research. Basic research is curiosity-driven. It asks, why does something happen? What is the underlying mechanism? And how does nature or society or a system really works? It doesn't necessarily begin with the objective of something commercial. On the other hand, applied research is more goal-oriented, and it asks how knowledge can be used to solve a practical problem. This can be industrial, it can be environmental, commercial, anything, clinical. But what I think is the most important when we compare the two fields is what is stated in my last sentence. The boundary between the two is porous. Basic and applied research are not two isolated things. They're not two islands that they are distinct. Okay, they feed each other. Basic research opens new possibilities. Applied research often reveals new questions that are fundamental and that we didn't think, we haven't thought of them up to that point. So this distinction, pedagogically, maybe it is useful, but practically, innovation usually happens at the interface of the two. The two fields need to interact in order to have something that it will create value and it will be innovative. Another distinction that I would like to make between, before we continue, is the difference between invention and innovation. An invention can be defined as the creation of something new. This can be a new method in a lab, or a new prototype, a new algorithm, a new material, anything. But this new thing, whatever it is, it can remain inside the lab. Innovation, on the other hand, begins when this novelty becomes meaningful in a certain context. It creates some kind of value, and this value can be economic, for example. It can be organizational. It can have an effect on society. So this is why adoption and deployment matter. A scientific result may be brilliant, may be excellent, but it becomes innovation only when it enters a system where we use it. This schematic shows Pasteur's quadrant. So this was first introduced by Stokes in 1997, and it offers a nice overview that will allow us to escape from the simplistic view, basic versus applied, because this is not the case. So on the one side, so we have four quadrants. Each one is named by a scientist or an inventor. So the first one is named Bohr, the other one is named Pasteur, the third one is named Edison, and the other one, the fourth, doesn't have a name because it's not important, it's not very significant. So on the one side, we have research driven mainly by the quest of understanding. Okay, so we have we have Maxwell, we have Schrödinger, we have Einstein. All these scientists asked for fundamental questions. They're examples of research that changed our understanding of nature before anyone understood fully any of the possible technological consequences. On the other side, Edison, for example, we have applied work under strong constraints with respect to usability. So we have product development, we have problem solving, we have engineering optimization, which is also very, very important. But this, the orange box here, is maybe the most interesting region in this Pasteur's quadrant. It is the use-inspired basic research. This is the point where we seek deep understanding, but in a context where use matters. Use is not irrelevant. So in this orange box, we have many transformative technologies living there. Okay, so we have quantum mechanics, but quantum mechanics leading to semiconductors. We have electromagnetic theory, but electromagnetic theory leading to wireless networks. We have nuclear magnetic resonance leading to MRI. We have the study of DNA structures, but leading to genomics and medicine. So the take-home message from this schematic here is that the strongest innovation systems protect the full spectrum, and especially the space between fundamental understanding and usage, the space where the two interact. By the way, feel free to jump in whenever you want. There is no need to raise your hand or anything. Jump in whenever you want to comment on something, when you have a question. It's absolutely fine to do this. So now let's move from the definitions that we gave to some stories. Our arguments will become stronger if we see how these historical chains evolve. So in this slide, you're going to observe a recurring pattern. Okay, I have 4 indicative cases: electromagnetic waves, quantum mechanics, DNA, and nuclear magnetic resonance. Of course, this is just a very indicative demonstration. So, what do we see here? We see that Maxwell, for example, wrote his equations in the 19th century, okay, in 1864. So this is 160 years before we had the development of our wireless civilization. On the other hand, we have quantum mechanics that they began as an attempt to understand atoms and radiation and matter. But in the end of the day, this started developing in 1913 by Bohr. But we had around 100 years before they became quantum technologies. Okay. Of course, before we had quantum theory becoming the foundation of semiconductors, which was a bit earlier, but computing, AI, and in the end of the day, any attendant technology relies on this. Then we have X-ray crystallography, which helped us reveal the structure of DNA. And eventually, this contributed to genomics and medicine. And of course, nuclear magnetic resonance became the method that is behind the basic diagnostic tool, imaging tool that we have, which is MRI. Now, what I want you to observe here is the time scale. 160 years, 100 years, 70 years, 35 years. So, what do we observe here? We observe that the time scale is long. But this is exactly the point. Basic research succeeds on a time scale that conventional innovation metrics do not capture. So, if we try to evaluate the results of basic research with, let's say, business metrics, we will always misunderstand. Because basic research operates on a generational time scale. This is the most important thing that we need to understand, and people who take decisions with respect to funding and research need to understand. It's not an immediate result. So I will start with my first story, which is the story of Maxwell and electromagnetic waves. So in 1864, Maxwell unified electricity and magnetism through the 4 equations that you may know or you may not know. It doesn't play any role here. The point is that this was not, this idea was not captured with the target of any product development. It was just theory. Later, Hertz demonstrated electromagnetic waves experimentally, and this is really ironic because Hertz was very absolute that, okay, this is useless whatsoever. There is no use on this thing that we call electromagnetic waves. But the thing is that electromagnetic waves could be produced, they could be detected, they could be controlled, and in the end of the day, they were available for engineering. So then Marconi, another guy, came and he used those waves to transmit signals across long distances. And this is the pattern. Science makes a phenomenon visible. We didn't know. Electromagnetic waves were there before us, but we didn't know. So Hertz made the phenomenon visible. And then engineering came into play and made it usable. So you see the interconnection of the two. Of course, this story is not over because the electromagnetic story continues now with 5G and 6G in I don't know in how many years. 5G is globally deployed now. We all use it. 6G is not standardized yet, but many enabling technologies around it are at the early stage with prototypes and testbeds, and we move toward higher TRLs, technology readiness levels. But let me comment on the 6G case because there are peculiarities that are important here and relevant. 6G is not simply faster than 5G. Because sometimes we think that, okay, we will have faster networks, good. But it is not only this. It is expected to combine communications, sensing, AI control, ultra-dense networks, reconfigurable environments, and maybe terahertz bands. So we don't have the usual transmission of waves as we had. We have been forming. So we will not just transmit energy broadly, but we will save electromagnetic energy in space. We are going to use reconfigurable intelligent surfaces to modify the propagation. And we will try to exploit terahertz communications that will push us into regimes that we do not fully control, because there we have absorption and scattering and other properties that make the whole case more difficult. And of course, it's not only this, it's also energy, because future networks cannot just increase the capacity by consuming unlimited power. We don't have unlimited power. So basic concepts like, for example, energy per bit and Shannon's theorem become very relevant. So the lesson, I spend a few more minutes on 6G because the lesson here is strong. So the more advanced the technology becomes, the more we need to return to the fundamental questions, because we need to address more difficult problems and maybe combine elements from different theories. Another deep example is quantum mechanics. So at the beginning, quantum mechanics was about understanding atoms, light, spectra, matter, etc. For reference, a quantum is the smallest discrete unit of something, of a physical quantity. In classical physics, these quantities appear continuous, but when we go to smaller scales and we examine small things like particles, the energy, for example, comes in small discrete packets that we call quanta. So quantum mechanics gives us several interesting notions. I'm not going to elaborate on these now, like superposition of states, like entanglement, ideas that initially are puzzling and deeply foundational, but they became the basis of modern electronics, and now they become the basis of quantum computing, So we have the transistor invented in 1947 by Bardeen and his group. He received the Nobel Prize, his second Nobel Prize for this. This depends on semiconductor physics. Semiconductors are materials that they lie between conductors and insulators. Okay? And they have peculiar, nice properties that we can tune. And that's why we can have the electronics that we have now. So from transistors, we get integrated circuits, we get microprocessors, and then we get personal computers, phones, the internet, AI, and okay, I will attempt this, and then digital twins. So why do digital twins belongs here? I'm talking about quantum theory. Why? Because a digital twin is not just a 3D model, and it's not just a visualization, a practical, nice visualization. A digital twin is a computational representation of a physical or a socio-technical system. This can include traffic, energy grids, building management, weather, air quality, even human behavior. And this makes the digital twin an example, a very, very nice example of a complex system. Complex systems involve interactive subsystems. They include feedback, nonlinear responses, and multiple time scales that we need huge computational power and efficiency to handle. So the connection from quantum mechanics to digital twins is long, but it's there in some sense because all the hardware that we need to do what we do with digital twins, we have it through the harnessing of electrons. So through quantum mechanics. Okay. I know that this connection that I'm trying to describe feels invisible now, but it feels invisible because computational power is trivial. We have it. We don't ask where it came from. It's there. Okay, now I'm talking all about physics, and this is not the case. Okay, I will talk for. I want to provide more examples, and this example shows that science does not follow disciplines and boundaries. So Watson and Crick solved the biological problem relevant to the double helix structure of the DNA. But in order to do so, they used X-ray crystallography, which made the molecular structure visible. So the diffraction data from Franklin were crucial because they showed the geometry that biological intuition itself couldn't provide. We couldn't just by intuition imagine what the geometry would look like. But with X-ray crystallography, which was developed decades earlier, this became possible. And the Braggs did not develop X-ray crystallography to build genomics, okay, or gene therapy, but this method crossed the border of the discipline, and it was used in biology, creating a revolution. The same pattern appears also in other treatments in medicine. For example, we use particle accelerators to understand the internal structure of matter. But today, we use accelerators for cancer radiotherapy. For example, we have PET scanners that use positrons. By the way, the existence of positrons was predicted by Dirac back in 1928, and he was developing a relativistic quantum theory, nothing to do with any application. But it becomes clear that these tools and concepts that emerged decades before, out of the concept of the medical technology concept, they play a huge role. They played a huge role in imaging, in radiotherapy, proton treatment, and so on. Another example, I will not stick here, I will not stay here too long, I don't want to tire you with all these, is optics and photonics. This was a very simple phenomenon, just the total internal reflection under specific conditions, and this showed that light can be guided through a medium. This was demonstrated in the 19th century, and back then, we didn't have any the attempt was not to build the internet. People just cared about showing how light behaves. But much later, and combining this technology with lasers and low loss fibers and optical amplifiers and so on, the whole thing became the backbone of our global communications. So when Kao and Hockman proposed the optical fiber for communication in 1966, it was a huge breakthrough, and that's why the Kao received the Nobel Prize in 2009. Check the time distance between the scientific advancement and when the contribution was actually recognized. So insights from basic science can take decades to mature. Okay, this is one thing that we understand from this. And the second one is that the second point that we can make here is that once it matures, however, it becomes, and if it becomes infrastructure, we just stop noticing the phenomenon. We have optical fibers. We don't check that this is based on internal reflection, total internal reflection. And my last example here is about a different thing, because it's not only physics and biology. This pattern is not limited to natural sciences. So we have auction theory asking a simple question: how should resources that are scarce be allocated when participants have strategic incentives, they have information, etc. It's not economics, it is engineering of decision making and engineering of institutions. So auction theory, along with mechanism design, practically redesign rules so that when people or firms act strategically and maybe they have conflicting interests, the overall outcome can still be efficient. And it can be also fair or socially useful. This is, since we discussed quite a lot about wireless stuff and 5G and 6G and electromagnetism, this became concrete when there were spectrum auctions. So spectrum is a scarce resource. Mobile networks, on the other hand, need spectrum. But the allocation of spectrum is not it's not simply a technical question. It is also an economic one. So auction theory and mechanism design shape the way that governments allocate these spectrum rights. Okay, and there was another Nobel Prize in 2020 in economics this time for improvements in auction theory and new relevant formats. Okay, with applications specific to the radio spectrum. So yes, 5G and 6G require electromagnetism, require science behind to exist as technologies, but they also require regulations. They require a market design, and they need a combination of all these things to become a deployable infrastructure. Okay, so deep understanding is not limited only to nature in the physical sense. It is applied to systems, to information, and also to collective behavior, to complex systems in general. So, three usual claims that are made when we have basic research discussions. The first is that basic research does not produce impact, but the historical record does not support this, okay, because GPS needs relativity, MRI needs an MR, and so on. The second claim is that basic research is inefficient because it takes too long. But again, this argument is not valid because it confuses timescales with inefficiency. If a scientific discovery takes decades to become the foundation of a new major technological ecosystem, that's definitely not inefficient. It's maybe long horizon value. And the third claim, often made is that researchers should focus in real-world problems. Okay, of course, real-world problems matter. But if we pre-specify, and especially people who make decisions about the direction of research, if we pre-specify the destination of what this research is going to be, then we narrow the space very much. We reduce the probability to discover something genuinely unexpected, which is going to provide something radically new. So this is a ladder of how, in my opinion, things should move. Okay, we do not innovate directly from ignorance. There are natural systemic phenomena. We need understanding to ask how something works. We need to control it afterwards, to harness the phenomenon, to repeat it, stabilize it, maybe manipulate it, and then design reliable systems around it. And then deployment comes. So can this thing that we created solve a real problem? And if yes, what is the impact? What is the value that it is going to create? This is the sequence of the questions that we need to ask in order to develop something new. Very briefly, a few things about emerging technologies that we have now, because to this point we focused on history. So what areas of today's science can become a platform for the next day? I have 6 fields here. I have quantum computing, quantum sensing, quantum key distribution, high temperature superconductors, neuromorphic computer, and photonic computing. And you see that I have included TRLs. TRL stands for Technology Readiness Level. I will explain a while what exactly this is. But the TRL stands for the maturity level of a technology. What I want to make clear here is that these maturity ranges, these TRLs, are not exact. They are indicative. And because we cannot give TRLs for entire fields. They apply for specific technologies, for prototypes, architectures, or use cases, but not for broad domains. But I use them a bit freely in order to indicate how close or far we are from something, from a commercial application. And some misunderstandings that we have. Because, okay, I don't know if you're familiar with the concept of quantum computing. We sometimes hear that everything will become faster and we will have super fast computers. This is not the case. Quantum computing will not make every problem faster. It offers potential, we don't know yet, speed ups for selected classes of problems, like quantum simulations or cryptanalysis. Neuromorphic computing is another very different idea, but very interesting and still at its infancy. And it tries to build computing architectures that are inspired by the brain. So using the architecture of neural networks, and the motivation here is energy. Because the brain performs control tasks and it uses a few tenths of watts. However, a data center that we use now use enormous power. So the neuromorphic idea comes to solve this problem by mimicking biological nervous systems. So being event-based and adaptive. But the hardware in this case is generally at a very low TRL, especially when compared to relevant software. So the field still lacks demonstrators and any real-world validation. Okay. Very quickly, I'm going to say a few things about what I consider the most transformative part of research that possibly will lead to a technology in a few decades. So I will focus on quantum technologies. Quantum computing, I said a few things before. We're not even close at the general purpose quantum computer. The quantum computer that is going to be fault tolerant and it will not be noisy and extremely limited. Today's systems are noisy and very limited. But we need to understand that the field is progressing. People create better hardware, they create methods to mitigate errors, and we have error correction at a quite good level. To indicate how young the field is, I will tell you that in 2019, Google's quantum computer Sycamore, the processor, I mean, performed a random circuit sampling in about 200 seconds. Okay. This was a very important result because the authors estimated that this would take a classical supercomputer around 10,000 years. So this was called quantum supremacy. Quantum supremacy is when a quantum computer outperforms a classical one, so it shows that it has an edge. But this was not a useful application. It was just a demonstration. So yes, scientifically, quantum supremacy is fine, but we are very far from any industrial application. The second category is quantum sensing. where we use systems as measurement devices. So an atomic clock, for example, can support GPS timing and make it extremely accurate. We can use quantum enhanced sensors that they will support navigation or subsurface mapping, medical imaging, and many more. But still, this is very at quite low TRLs. The third category is a bit more advanced, and it is about quantum communications. So we have quantum key distribution, which uses principles of quantum measurements to detect eavesdropping in specific settings, communication settings. By no means this is a universal replacement for cybersecurity. It is completely complementary to post-quantum cryptography. But it shows how we can combine quantum optics, Bell's theorem, and information theory to move towards a commercial system like the ID Quantic. This is a company that was founded in 2001, and it is actually a company that uses this quantum key distribution as its main product. Okay. So the quantum technology ecosystem is not one technology, but a family of things. So this is the last part of this talk. Where I'm going to discuss about readiness, knowledge transfer, and the innovation chain. So how practically now we can take these ideas and move forward to something applied. So TRL, as I mentioned before, stands for technology readiness level. Okay, so as we grow in TRL, the closest we go to the market. So TRL1 is when we first observe the basic principles. TRL2 is when we capture the technology project. TRL3 is the proof of concept. And then we move to lab validation, relevant demonstrations in specific environments, prototypes, etc. The key idea is that the early TRLs, the blue ones, cannot be shortcut. We cannot jump from a physical principle to a deployable product because we just want to do this. We need all these intermediate, initial and intermediate steps. And it is interesting that many ideas die in this green area here, which is called the Valley of Death. They don't die because they're bad ideas. They die because they do not have a home, an institutional home, when they do the transition from proof of concept to a validated demonstrator. So this is one of the reasons that knowledge transfer and proof of concept funding becomes very important. But okay, technology readiness level is one thing. I have it here with a tick, if you can see, but technical readiness and technological readiness is not the same as innovation readiness. So TRLs answer one question. Does this technology work? And in what environments should we demonstrate it and use it? But innovation now asks more questions. Is there a user? And if we develop it, will we find a market or somebody from the public sector? And what is the regulatory conditions here? If we proceed, is there a concrete business model? And what about then sustainability, either this sustainability is environmental or financial or social. So a technology may be technically perfect, but it can still fail. Because if there is no adoption, if there is no pathway, no infrastructure, and no regulatory framework or a financing mechanism, then it cannot proceed. So the digital twin concept, okay, we have, let's say that we have a demonstrator, but who will maintain it? Who is going to own the data? Which municipality or company will adopt it? These are very relevant questions when it comes to deploy a solution. And this is where, and this is exactly why innovation readiness is a multidimensional thing. This is the valley of death here that I told you before, between TRL 4 and 6. It's not a funding gap. Don't misunderstand it. This is not just a funding gap. It is often a translation gap. So a result may be too mature to be pure research, but not mature enough for industry adoption. It may need validation or a strategy regarding intellectual property. So this valley of death is where research needs a bridge between proof of concept and following steps. And this is where technology scouting becomes relevant. And exactly this is my point here. We explain why high TRLs may fail, because the problem is adoption. Users may not understand the value of what we created as scientists, or they may not trust the system, etc. And so we have missing translation environment between research and adoption, relevant to sustainability, relevant to economics, relevant to context. So the issue here is not just technology by itself, if it works or not. We use a certain range of things like rules, infrastructure, and trust. So knowledge transfer and technology scouting provide this bridge to identify maturity, select pathways, test value, and build an adoption context. So knowledge transfer. Knowledge transfer can be the bridge between knowledge creation and real world use. The upper row here shows the process. We begin with the scientific insight. We assess the knowledge, what is new, useful, etc. We select a pathway. We move toward adoption and deployment, and then we examine the social impact that it can have. The lower row shows the possible pathways for this knowledge transfer. So not every research becomes a startup. Maybe we need further research. Some results may need, for example, the proof of concept. Other results may need licensing. In some cases, we have spin-offs. Okay, so it is a different thing, the knowledge transfer process and the possible transfer pathways. And as we approach to the end, this is the technology scouting case that also is a very important bridge to skip this valley of death. Practically, technology scouting is a mechanism that connects what the project knows with what society, industry, or the public sectors may need. it starts from research outputs, it screens them, it examines which outputs have potential, which outputs are at a very early stage, etc. And then it assesses readiness, technical readiness, innovation readiness, and all the previous steps. Then it selects an exploitation pathway, and finally, it leads to action. For example, action could be that we need further research, or that we need to create a demonstrator, or that we need to create a spin-off out of this. Technology scouting practically asks which of these outputs can move toward deployment, and which need further validation. So this is a practical innovation check, questions that you can ask when you want to address whether your research could be something deployable and usable. And before I close this talk, and thank you all for being here, I want to share a thought that has been in my mind for some time now. And it is about information, because I talked about information, and it is about how the definition of information changes, and how these changes lead to paradigm shifts, and how the paradigm shifts lead to new knowledge, new concepts, and maybe new tech. So for Shannon, information was uncertainty. When information became measurable, we were able to compress it, transmit it, protect it from noise, and this is how we built our modern communication, the whole system. Then quantum mechanics changed this concept. Information was no longer a message moving through a channel, but it could not be destroyed. Okay, it could be delocalized, it could be hidden in correlations, but it cannot be destroyed, it cannot be lost. So this is a very different this is an important qualitative difference from classical information theory as we use it. So quantum information is no longer about what an observer learns from a message, but it is about what we can encode physically in a system, and then encode and then transform it, recover it, etc. So this shift in the paradigm, this new definition, this is a new definition, and just a new definition opened the field of quantum information and quantum computing and so on. And I was thinking that today the frontier, of course, this is not settled science, but it is the frontier in theoretical physics, goes even deeper, and it examines the possibility that information, maybe it is so fundamental that it doesn't exist in space-time, but space-time emerges through informational processes. I'm repeating, this is not something that we know, it is a hypothesis. But we can see the progression. So Shannon helped us define the modern and digital communication age. Quantum information opened our horizons toward quantum computing and all these new technologies that we will enjoy in a few decades, possibly. And now we have a new idea that information could be the foundation of space-time. And this may be pointing toward the new conceptual frontier with technological consequences that we do not even imagine. We cannot predict, we cannot even imagine. We don't know. But this is the point. We do not know what a new concept will become. Shannon was not designing the internet. Bohr and Dirac, they were not designing quantum processors. And people who elaborate on this idea, they are not designing any product. But by changing the way we define the fundamental concept, maybe we may be changing the boundary of what a future technology can become. Thank you very much. If you have any question, I'm all ears.